Hello, today we want to look at derivatives. So just take a little regression. We just go back one little bit and just look at the definition of continuity. So here we are. A continuous function. A function is continuous if this happens. The function will be continuous if one, if the point z is equals to z naught. If the limit approaches if z approaches f z naught is the same as the value of the function at that point. So it basically means the limit and the function itself give you the same thing. So it will be continuous at every if that happens at every point. So continuity is a pointwise property. It depends on the point where it is defined. But if it is continuous at all the points in that domain, then you say the function is continuous. So continuity, because it derives its properties from limits. It also has the same characteristic as what limits have. So if two functions are continuous at a point z naught, then the sums of the functions are going to be continuous. The product of the functions are going to be continuous. And then, as long as the denominator is not equals to 0, the ratio of two functions is also going to be continuous. So let us look at one typical example, a simple one. We have this function defined by f of z. F of z is equals to. So in the numerator there, we have the real part of the function. So you are squaring the real part of the function, and then you divide it by the modulus of z squared. This is at the points where z is not equals to 0. Then, but at the origin, you define the function as being equal to 1. So the question is this function continuous at the origin? Let us just look at that. We are going to look at the origin, and then determine whether the function is continuous at that point. So, taking from the definition, what we need to do is just find the limit of the function at the origin if it exists. And if that limit exists, it should be equal to the value of the function at the origin. So it means it should be equals to f equals to 1. So let's take that. So we know that the real part from complex numbers, the real part of the function z is x. And we know that if you get the modulus of z squared, you get x squared plus that. So we substitute for this into the function. If you substitute into the function, it's the real part squared in the numerator divided by the modulus of z squared. So the function, it becomes this. So to calculate the limits at the origin, let's approach the limits along the axis. So you can approach along the x-axis, the horizontal axis. On the horizontal axis, x is equals to 0. So you substitute into this function for x equals to 0. So you have this is 0 and 0 over 0. Because the numerator is 0, it doesn't matter what happens in the denominator, it will still be 0. Then you want to approach this now along the y-axis. So along the y-axis, this is what happens. Along the y-axis, y is equals to 0. So it's only the y that is going to be equals to 0. So in this case, it's going to be x squared over x squared plus 0, which is equals to 1. So in this case, the limit approaches two different values. Along the x-axis, it is 0. Along the y-axis, it is 1. Along the y-axis, it is equals to 1. So in this case, the limit does not exist. So the limit does not exist. So since we don't have a limit, we cannot talk about continuity here. So the function is not continuous. So that function is not continuous because the limit has failed to exist. If the limit had existed, it could have been a different story. So uh, now we go to the matter of this lecture. Uh, just after regressing to continuity, the matter of this lecture is about differentiability. Now remember, derivatives are defined as a limit as well. We mentioned this before. Uh, the derivative, if you add a point z is equals to z naught, then you say z is differentiable at that point if the limit, which we call the derivative, if this limit exists. So the derivative is the limit if delta z goes to 0. If the limit is the limit if delta x goes to 0 of f of z naught plus delta z minus 1. So you remember how we defined this, even for real functions. It is just the short code. You join 2 points, points z and z naught, and you approximate the gradient of that line. So this is just like the change in the x over the change in y. So it's just basically the same. So if it is differentiable at every point in the domain D, then you say the function is analytic. So an analytic function is a function that is differentiable at every point in the domain D. Then it is analytic at a point z naught if it is analytic in a neighborhood. So if you are just around that point, that's what we call a neighborhood. If you're just a small distance around the point, then you have a function being analytic at that point. And a function that is analytic on the entire complex plane, on the whole complex plane, is called an entire. So an entire function is analytic everywhere. There is no point where it is not analytic. So there are a lot of elementary functions which are analytic on the whole complex plane. On the whole complex plane. So we'll look at this later on. But let us go with this definition of derivatives and give you a few property and give you a few one example. So let us find the derivative of this function. The function is f of z, which is 1 over az plus b. If you want to get that, we just need to use the definition. So what we have is that if you have f plus delta z minus f of z, it is going to be the limit. You just replace z with the z plus delta z in the first part. So it will be a times z. So it will be a plus b delta z. I think you close it here. Then plus b. And then you subtract 1 over b, which is that the function itself, and you divide by delta z. So if you do that simplification, bringing everything in the numerator here under their common denominator, which is this. This is the common denominator of the numerator there. This is the common denominator of the numerator. If we have that, then you are going to have 1 over delta z as the divisor. Take it separately. Simplify this. I think az, you can see az will cancel with az, b will cancel with b. What will remain in this case, what will remain in the numerator is just minus a over. You have minus a in the, because there will be an a times delta z here, and then you divide by delta z. So in the numerator we have a. So I always implore people not just I implore people to actually try these things on their own. Work through this and get satisfied with every result that we're getting, which we're getting here. Because if you don't follow it on your own, if you don't get it on your own, then you're in trouble. Just make sure that you do it on your own. So, because we can't fit all the details in a small slide like this. So we will give you the key results. So if you now let the derivative, to get the derivative, we have to evaluate this limit. So we are letting delta z go to 0. So I say, I've always mentioned this. It's the first port of call of evaluating for a derivative is to just try substitute this and see whether that works. So if you substitute delta z is equals to 0, we are going to have a 0 here. So what you have here and here are going to be the same. So the numerator will be just this squared because there will be no z here. So it is equals to minus a over z plus b. So that is the derivative of this simple function here. The derivative of that function is this. So it's a simple calculation, and it gives us that. So we talked about whether at a point that the derivative exists. So for this one, the derivative exists. Let us look at the next example. Let us look at just a remark about continuity and a derivative. So a differentiable function must be continuous. So it has to be continuous. But, however, if the function is continuous, it does not mean that it is differentiable. So we have this proposition. We are saying that if you have an open set, which is just an open set, an open set is a set which is not closed to the edges. It does not include points on the boundary. The points on the boundary are excluded. So if it is differentiable at a point inside an open set, then the function is continuous. So it's the other way. Differentiability implies continuity, but continuity does not imply differentiability. So if it is differentiable, the function will be continuous at that point, but not the other way, according to this remark here. So we are going to look at some properties of differentiable functions. Derivatives, we defined them using limits. So they will inherit properties of limits. So the derivatives of the sum will be the sum of the derivatives. So for plus or minus, you get that. If you differentiate a constant multiple, it will be a constant multiple of that function. So you can factor out a constant multiplication. So if you remember from our first course in engineering mathematics, if you have addition and multiplication by a scalar, you have a linear function. So the differentiation, the operation of derivatives, is a linear operator. It's a linear transformation. The number one and number two are what we had for linear functions. Then the third one is on products. If you are defining a product, this is the product rule. What will happen is you keep your f and differentiate g. Then in the second one, you keep your g and differentiate f. So you have number three is basically what we called the product rule. Number four is the quotient rule. If g of z is not equals to 0, you have the quotient rule. This is the rule that we use to differentiate rational functions. Yeah, we were using this as a u over v for real functions. So it is the same rules for calculus of real numbers apply with the calculus of complex value. Then the number 5 is what we call the chain rule. If you are going to differentiate a function of a function, it is going to be the derivative of the function itself first, and then you multiply by the derivative of the argument, which becomes that. So we say that if it is analytic. To say a function is analytic for complex valued functions, it only means that it is a derivative. So when we talk about analytic functions, we're just talking about what are called differentiable functions, functions that have derivatives. Those are what we call analytic functions. So, in some cases, for analytic functions, people are they're given a special name. They are called holomorphic functions. You might encounter this if you read other texts. They are what we call holomorphic functions. They are just analytic functions, functions which have derivatives. Now, let us have an example, because we're saying a function is analytic, and then let us look at an example of a function that might not be analytic. So it's a very simple function. The function f of z, which is just z bar. So this is just a function where you are conjugating it, the function. You take your f of z and then find its conjugate. So you want to check whether that function is analytic. We are showing here that it's not analytic anyway. This function is just going to be analytic only at the origin. Elsewhere, it's not analytic. It means that this function has a derivative only at the origin, but not elsewhere. So let us look at this. The derivative, and the derivative itself is just given as how we define it. If we use that and substitute, we just want to find the conjugate of the function at z at this point here. So we are going to do it at z plus delta z. And then we substitute that. I think I just substituted this with the z naught. So if we substitute that, the conjugate of a sum is equals to the sum of the conjugates. You get that here. Something that we can show for complex numbers. So what will remain is that this first one and the last one will cancel out. Will remain with the conjugate of delta z. Now we know z is equals to x plus iy. So its conjugate, it's delta x plus delta I plus I delta y. So the conjugate, you change the imaginary part, the sign of the imaginary part. Delta z, what we had in the denominator, is what we found is conjugate in the numerator. So this is delta z in the denominator. It's just given by that. So let us now evaluate this. So I think we just want to let delta z go to 0 and delta y go to y, because that's what it means, delta z go to 0. It means delta x will go to 0, delta y will go to 0. So we will now follow what we have been doing for the last few examples. The easiest way to check for a limit if it is going to exist is to check along the axis. So if you check along the real axis, we'll see that delta x will go, you substitute delta y is equals to 0, and you get delta x over delta x. The imaginary parts disappear in this case. So you are going to have the limit, because if you divide this is just going to be equal to 1. So if along the x-axis, the real axis, it is going to be 1. Then along the imaginary axis, we have this. If you start, the real parts are going to be 0. It's only the imaginary parts which are going to be there. If you look at what we had, this one, it changed its sign. So it is going to be minus 1. So we obtain different values in this case. So the limit does not exist. So it implies that if the limit does not exist, the definition of a derivative is that the limit should exist. And the value of that limit is the derivative. So it implies that the function is not analytic. So there we go. I think here we'll look at how we. So in the last example, we had an example of a function which does not have a derivative. But I think if you look at the origin, if you substitute at the origin, the derivative will be equal to 0, and the function will have a derivative. Now, Here we have just a little extension of derivatives. If now your function is a function of two variables, if a function of two variables and you have you define this as a Jacobian, and usually it's just the distance between the 2 points. It means if you want to find the derivative of a function of two variables, you have to have the distance between the 2 points being small. That is what this slide is just telling us. So we'll not worry much about that, but when you come back to multivariate functions, we'll consider that. So we're going to have that later on. So let us continue now with what we want to do for the functions of one variable, for our function z. So here is the issue. The issue is to try to see whether a function is differentiable or not. So the result that we use about differentiability, checking whether a function is analytic, is a two simple equations which we attribute to Augustine Koch, and Bernard Riemann. Bernard Riemann, I think this is about 18 something, which is we call during the Victorian era in the 18th century, in the 18th century. Yeah. I think that's right. We call it in the 18th century. So about 100 or so years ago, more than about 150 years ago, that's when this result was derived. So it says that if f is differentiable, then the partial derivatives of u and v exist, and the derivative matrix is given by the Jacobian matrix. The Jacobian matrix is just this matrix which we have just discussed. So the Jacobian is just the determinant of this. You just find the determinant of this, and it will give you a derivative. So if you have that, then the Jacobian will exist, and you get the derivative of that. Now, if the partial derivatives of u and v exist and are continuous, then f is differentiable. Because we said here, we want to look at when is it differentiable. So if you can find the derivative of this one and find the derivative of the real part and the imaginary part, and they are continuous, then that function is differentiable. So this is the theorem that we are going to use, the Cauchy-Riemann equation. So for any set, for any domain where it is defined, and this function, which is f of u, if it is differentiable at a point, it is differentiable if and only if f is differentiable at that point in the sense of real variables, and the functions u and v satisfy the Cauchy-Riemann equations. So these equations tell you whether the function is differentiable or not. So in a way, they tell you whether the function is analytic or not. So the function is analytic if we differentiate. This is a partial derivative. If we differentiate u with respect to x, and you get the same thing as the derivative of v with respect to y. And that is also the same as the derivative of u with respect to y, which will give you the negative of u with respect to x. So the idea is this: in the first one, the u with respect to the imaginary part with respect to the real part with respect to the real integral, and the imaginary part with respect to the, if you just do a real to real, imaginary to imaginary, they should be equal. But if you do real part with respect to imaginary, and imaginary part with respect to real, you just get the signs will be different. The signs of the two things will be different. So that's the Cauchy-Riemann equation. Most books and most books derive them. So let us look at one example where we use the Cauchy-Riemann equations. So we have to determine whether this function, the function which is 1 over z, whether this is analytic. So what you need is just an expression of that function in terms of u and v, real and imaginary part. So if we express that function, it is 1 over x minus y. We multiply the numerator and denominator by the conjugate. You get x minus y. The denominator becomes x squared plus y squared. It becomes a real function. So our u, which is just the real part over this denominator, is this. Our v, is equals to, I think this is just a small typo. Our v is equals to minus y over x squared plus y squared. So if you want to test the Cauchy-Riemann equations, we take u, differentiate it with respect to v. So this is, you use the product rule, the quotient rule, and you end up with this, because here you end up with the y squared, but there will be two of these, and there is one of this. So there are two negatives, so y will become negative. So du dx becomes that. You differentiate with v with respect to y, the quotient rule, and you get this. So the first Riemann equation is satisfied. So check this. Do this on your own. Do this on your own, because I think mathematics is just it's not a spectator sport. You don't learn mathematics by just watching other people do it. You have to actually do it on your own and check whether that they are correct. And the moment you actually have a feel of it yourself, then you'll grasp it. If you just watch anyone doing it, you will not get it. So we now go for the second Cauchy-Riemann equations. Now we now differentiate the real part of the function with respect to y, which is the imaginary. So if you have that, it will be minus 2xy. Then you differentiate dv with the imaginary part with respect to the real part. If you have that, then you have 2xy over x squared plus y squared. So the second equation is satisfied, because these two have different signs. These two have different signs. If they have different signs, then they are equal. So this is the negative of that. So those two are satisfied. So it means that the function that we started with, this 1 over f of z, is analytic. So possibly it's analytic everywhere. I think we can only have a problem when z is equals to 0. So it's analytic everywhere. It's possibly mentioned that except at the origin, where the original function is. But wherever it is defined, it is analytic. So Cauchy-Riemann equations determine for us. We use them to determine whether a function is analytic or not. So having looked at the Cauchy-Riemann equations, the Cauchy-Riemann equations are related. They determine whether a function is analytic or not. But they also give us a new tool to analyze what we have, what we call harmonic functions. So harmonic functions occur in a number of physical phenomena. I think in heat transfer and whatever in heat transfer, vibrations and other related things. I think mainly with the heat transfer, you get what we call harmonic functions. So harmonic functions, yeah, then vibrations. I think the name where you have harmonics in music, so the vibrations would vibrate in a particular way, which is called harmonious and so forth. So that is physical meaning. So let us look at what we call these harmonic functions. Now, these harmonic functions satisfy what is called Laplace's equation. So the Laplacian is an operator where if this operator, you take the second order derivative with respect to x and the second order partial derivative with respect to y. These are just partial derivatives. And if a function delta, a function phi, this is the Greek letter phi, which is in the equivalent of f in our alphabet, in the Latin alphabet. Phi, if you can differentiate it twice, that is because you would need to have second order derivative. Then it is harmonic if the different the Laplacian is equals to 0. So harmonic functions will be functions where you have the derivatives being equal to 0. The derivative being equals to 0. So for the time being, I think let's check what we're going to have next. So I think we're going to have harmonic functions. So we'll skip that for the time being. We'll leave that for the next short of our lectures. So for harmonic functions, that's where we are going to take off in our next lecture.